Hello, and welcome to The Usefulati, the show that turns the writing of the world's most useful people into audio episodes you can listen to on your drive to work. Today, we have a blog from Casey Handmer, the founder and CEO of Terraform Industries, a startup that's turning water and air into carbon-neutral natural gas with solar power. See the description for more, and let's jump in.
Part of the series on common misconceptions in space journalism, a follow-on from a previous post on terraforming. As far as terraforming goes, I've recently been much more occupied with my startup Terraform Industries, but it still generalises to creating technical and economic ways to continue the ancient human project of gardening our surroundings to be less unpleasant. By the time Terraform Industries has completed its mission on Earth, we'll have finally assumed intentional and granular control over the world's carbon cycle and parts of its water cycle, and in turn its position of radiative equilibrium with respect to the sun. In other words, controlling the climate deliberately rather than accidentally. There are certain ethical quandaries associated with assuming this level of control over the world's systems. But it is important to remember humans have always modified their environment to the extent possible, including measurable impacts on climate that date to prehistoric times, from forestry and hunting megafauna to extinction. What we can say is that atmospheric hydrocarbon synthesis will deliver more equitable, cleaner, cheaper energy at much lower environmental cost than the existing approaches. The subject for this post is not Earth, but Mars. Mars is cold, dry, dusty, and, in its present state, downright hostile to life. Part of the reason for this is that Mars is smaller than Earth and further from the Sun. Yet Mars was warm and wet in the past, initially for an extended period shortly after its formation, when the Sun was seemingly too cool to produce enough heat. And later, perhaps in hundreds or thousands of discrete episodes, the planet seems to have flipped between relatively short periods of active water cycling with oceans, lakes, rivers, rain and snow, intermediated by longer dry spells, such as the one in which we find the planet today. It seems likely that these two states are relatively stable, though their relative prevalence would suggest that warm and wet deterministically reverts to cold and dry after a short period, perhaps due to mass high-altitude glaciation on Tharsis leading to a runaway drop in albedo and reduction of water available to feed the water cycle. Even a warmer and wetter Mars would still be hostile to life, as its atmosphere would be almost entirely carbon dioxide and still relatively thin. But warming the planet and filling its lakes and seas is the first step along the way to finally achieving open skies with breathable air, and it's the step I'll talk about today. What active steps can humans take to flip the planet into a warm and wet state, and ideally stabilise it there over meaningful timescales? As described in my previous blog, among other sources, a number of methods have been discussed for terraforming Mars, including deliberately crashing an asteroid into the planet, nuking it, building autonomous greenhouse gas factories on the surface, and solar sails. Some of these are more plausible than others in terms of sheer technical feasibility. The key point, however, is that given time and capital scarcity, it is meaningful to ask, which method will give me the most additional watts per dollar? In terms of heat available on Mars, the dominant source is the Sun. At Mars orbit, the Sun drops roughly 600 watts per square metre onto the surface, or 21,600 terawatts over the entire planet, which is millions of times more than one could achieve via, for example, running a series of nuclear reactors and dumping the heat. The trick is to find a way to enhance solar heating, hopefully inducing a runaway greenhouse effect. Under this model, initial efforts warm the planet to some critical level, which results in the atmosphere thickening enough to trap more heat, which in turn warms the planet with no additional further effort. The greenhouse gas factory method produces powerful heat-trapping gases, such as perfluoropropane, whose absorption spectrum neatly plugs the gap left by carbon dioxide and has millions of times more heating power per unit mass of gas produced than carbon dioxide. The major drawback of this approach is that it requires substantial mines and gas factories emplaced on the surface, small compared to terrestrial mines but large on a planet where humans have, to this point, excavated only a few cubic inches of material. If there was already a sizable human population on Mars, with some local industry, this would be merely extremely difficult. An entirely automated, self-replicating, nuclear-powered, robotic perfluorocarbon factory is, in my view, science fiction. Such a project could easily consume $1 trillion and half a century in research and development before the first landing, let alone the first burp of enhanced greenhouse gas. In fact, when contemplating different options and the current and future discount for performing some operations on Earth, which has copious quantities of labour, materials, breathable air, and a well-developed supply chain, I became interested in whether it would be possible to start the Mars terraforming process with zero in-space manufacturing or new technology. It is possible, and unsurprisingly, basic calculations show that it would also be by far the cheapest approach. This is not so different from the observation that the cheapest way to provide power to a lunar base is to beam it from Earth. I will describe the basic idea and then explore the implications in some detail. The pitch is to mass-produce small-scale solar cells in terrestrial cell phone factories, launch them into low Earth orbit, and have them fly themselves to Mars, where, hanging out near Sun-Mars Lagrange Point 2, they would reflect additional sunlight onto the night side of the planet. I first wrote about this 4 years ago. Solar sails are a little different from other kinds of spacecraft, and as of this writing, 4 have been launched and operated in space. At 1 astronomical unit, they generate about 8 micronewtons per square metre. Aerial density therefore determines their maximum acceleration. For a 1 gram per square metre sail of very thin aluminized mylar, maximum acceleration is 8 millimeters per second squared. This is about 0.001 times the acceleration due to gravity. But there are a lot of seconds in a day, in principle 700 meters per second of change in velocity per day. There are confounding effects, but a sail with modest performance would be able to escape Earth and fly to Mars in a matter of months. Since atmospheric drag is also proportional to area, there is a minimum altitude, roughly 800 kilometers, below which solar sails will not be able to escape the Earth. Rotation can be used to deploy, steer, and stabilize a sail, but also has complications, such as weird dynamics and a need for axial precession to maintain angle of attack while spiraling out of low Earth orbit. Each sail weighs 1,000 grams and covers 1,000 square meters. So think of a cell phone that is mostly made of very thin space blanket, unfolded to cover a couple of basketball courts. At current prices, launch cost would be around $2,000, while basic cell phone manufacturing cost is about $100. Long-term, both these numbers could be reduced quite a bit. A Starship-launched sail with even thinner sail material, weighing just 250 grams, might cost only $50 to launch, while aggressive value engineering to remove superfluous features could see manufacturing cost fall to a similar value. For example, the solar sail needs a processor, camera, star tracker, and basic telemetry radio. 2 watts is plenty for weak signal propagation, reporter-like error correction. It also needs the sail, some kind of large liquid crystal display panel, to alter reflectivity and enable steering, and a solar photovoltaic cell for power, but it doesn't need a display, buttons, lots of flash storage, an impact-resistant chassis, or, it turns out, a battery. No miracles are required to fit the entire electronics package into a printed circuit board the size of a basic Arduino. 1,000 square meters at Mars reflects roughly 600 kilowatts of additional heat energy toward the planet. So for this system, the marginal cost per megawatt of heat is between $160 and $3,500. A Starship launching 150 tons would deliver 600,000 solar sails, or nearly half a terawatt of extra heat for just $60 million. Foxconn and others produce hundreds of millions of cell phones every year. So if our solar sails tap the same supply chains and manufacturing processes, it should be possible to ship more than 100 terawatts of additional power to Mars every year. Mars' cross-sectional area is about 36 million square kilometers. 1,000 sails add 1 additional square kilometre to this tally. 150 million sails per year adds 150,000 square kilometres, which is a 0.4% increment in solar forcing. It is uncertain exactly how much extra heat is needed to heat Mars to the point where volatiles outgas from the regolith and trigger a positive feedback loop, preventing radiative heat escape. But even if we brute force it, a decade of launches will increase the effective solar collection by 4%, and, with 1.5 billion sails above Mars' night sky, the view would be spectacular. As a rough estimate, a 4% increase in energy input would require 4% higher thermal radiation to achieve equilibrium, which, depending on some geometric factors of order unity, would result in a 1% temperature increase from 210 Kelvin to 212 Kelvin. This is twice what we've achieved with 250 years of industrial effort on Earth, burning 1 trillion tons of fossil fuels. In fact, a solar sail placed near Sun-Mars Lagrange point 2 would have an apparent magnitude of about negative 0.75, similar to Polaris or Saturn, while billions of them filling a cloud with an angular extent of about 5 degrees would have thousands of sails per human eye pixel, creating a cloud of light like the Milky Way, only a substantially brighter echo of the reflected sun. While the surface brightness of this cloud would be only roughly 0.1% of the sun, the integrated brightness would be more than Earth's moon when full. We can be smarter than diffuse light brute forcing. Given sufficient control of our sails, we may be able to focus the sun's heat on discrete locations on the surface of Mars, heating and calcinating ancient carbonate deposits and greatly increasing the quantity of carbon dioxide available for warming. The problem is all about leverage, and a watt of power directly reflected is good but not as good as a watt of power spent releasing a couple of grams of fresh carbon dioxide every hour, in addition to its own heat. There are 2 additional points of interest to be covered: Earth orbit and Mars orbit. On departure from Earth, the solar sails need only be launched high enough that the net thrust from solar pressure, which scales with the area of the sail, exceeds net drag from the sail in the upper atmosphere, which also scales with the area of the sail. In practice, this is about 800 kilometres, which is higher than the International Space Station, but lower than the Iridium constellation. In order to enable continuous power and orbital boosting, the sails must be launched into a polar sun-synchronous orbit. These orbits form a family where Earth's equatorial bulge causes precession that matches Earth's rotation about the Sun. As sun-synchronous orbits match Earth's 24-hour day rather than the 4-minute shorter sidereal day, they enable passes with consistent illumination and are popular for Earth observation. Sun-synchronous orbits typically have an inclination of about 96 degrees, which increases slightly as perigee increases. In practice, our sails will be in high enough orbit and raising their orbits quickly enough that even though they have sufficient thrust to adjust their inclination, they don't actually need to. If they accelerate away from Earth quickly enough, over a few months, then their orbit need never pass through Earth's shadow, removing the need for the complexity of batteries. Once out of Earth's sphere of influence, they employ the same orbit-raising tack to track outwards towards Mars. Using their small but continuous thrust, they can be launched any time, regardless of launch windows, to arrive at Mars between 9 and 18 months after launch. Once at Mars, the sails heave to near Sun-Mars Lagrange point 2 without getting anywhere near elliptical. Mars orbits or Mars solar eclipse, which would shade the sail. Lagrange point 2 is one of 5 Lagrange points, or points of relative gravitational stability, in a two-body system. Sun-Mars Lagrange point 2 is found about 1 million kilometres further from the Sun along the Sun-Mars radial. In this location, Mars gravity adds to the Sun's enough that the orbital period is the same as Mars, even though a body at this radial distance from the Sun would generally have a longer period orbit. At this distance, Mars' angular extent in the sky is about 0.007 radians, slightly larger than the apparent size of the Sun, which means that no sail convexity is required to have Mars absorb all the reflected light from any given sail. Lagrange point 2 is stable in the axial plane, perpendicular to the radial, but unstable in the radial direction. This is why the James Webb Space Telescope's orbital insertion needed to be so precise. Lagrange point 1 and Lagrange point 2 satellites generally orbit their respective Lagrange points, forming a quasi-circular path around the radial that can generalize to the interplanetary transport network. In other words, satellites at Lagrange point 2 can occupy a substantial volume of space where their orbits are stable enough. For solar sails, we need to generalize a little bit more, since the sails, once on station, would ideally live in a zone where solar pressure, centrifugal force, and gravity from the Sun and Mars are in balance. Since solar pressure provides an additional force outwards, the solar sail Lagrange point 2 zone is somewhat closer to Mars. And since the solar sail can adjust its force vector by changing its angle, the zone is quite large. We further restrict this zone to places where light reflected from the sail falls on Mars' night side, and are left with a set of surfaces parameterized by the areal density of the solar sail. Despite this restriction, the volume available for sails to live is enormous compared to the surface area of a planet. So it is highly unlikely that even uncoordinated sails would ever collide or even shade each other. It turns out that new technology, propulsion, space-based hydrogen bombs, and Mars cities need not be on the critical path for terraforming Mars. It cannot be overstated how much cheaper and easier it is to do as much of the mission as possible while still on the ground. Even if people living on Mars wanted to terraform the planet, the cheapest way would be to contract Earth-based groups to spam the Mars night sky with solar sails.